3.4 is about the zeros of polynomials. So let's remember what zeros are. Zeros are the solutions to the polynomial. They're also called your x-intercepts. It's where it crosses our x-axis. So we can use a rational zero theorem to figure out how many zeros. So with polynomials, we may have more zeros than, like with a quadratic, you could just have it where it crosses the x-axis at one point. That'd be 1, 0. You can have it where it crosses at 2 points. Or you can have it where it has imaginary zeros, where it doesn't actually cross the x-axis. So we have 1, 0, 2 zeros, and no zeros. So the same thing is true for polynomials. So our polynomials, they'll have more than just the one curve like a quadratic has. So we've got to know how to find out how many zeros it can have. So it could have 1, 0, 2, 0. Could it have no zeros? It depends on how it's set up. But these are options. But also it could have 3 zeros, 4 zeros. It kind of depends on what the degree is. So we have a theorem that'll help us find out how many zeros there are. So that'll help with our guessing. So we don't have to guess as much. We will know, okay, we have 3 zeros, and here they are. Okay, so this is called the rational zero theorem. Okay, so the rational zero theorem will help us find out the zeros. So we are going to find out the possible number of zeros is equal to factors of the constant term divided by factors of the leading coefficient. So these are the possible number of zeros. So this is the rational zero theorem. So let me go ahead and give you an example. Let's figure out how many possible zeros are in x to the 4 plus 3x squared plus 4. Oh, it's a negative x to the 4, sorry. And I should write it as f of x. So our possible zeros will be the factors of the constant term over factors of the leading coefficient. So our constant term is the 4. And so we need to list out our factors of 4, positive and negative. So we know 1, 2, and 4. But since we want positive and negative, we can list these as positive negative 1, positive negative 2, positive negative 4. And then our leading coefficient is a negative 1. And our factors are just positive, negative 1. Okay, so now we write it as each one of these over our leading coefficient. So it'll be positive negative 1, positive negative 2, positive negative 4 over positive negative 1. And then we'll list them out individually, and that'll tell us how many we have and what they could be. So positive negative 1 over positive negative 1 would be 1 and negative 1. And then positive negative 2 or positive negative 1 would be 2 and negative 2. And then positive negative 4 over positive negative 1 would be positive 4 and negative 4. So we have 6 possible zeros. It should really say 6 possible rational zeros. Because, we have rational and irrational. So we are just going to talk about rational zeros right now. Then we have real and imaginary. Okay, so there are 6 possible rational zeros. We can look at the graph to find those. So let's get out our calculator. Let's plug this in to find the actual zeros. So we'll put in our function negative x raised to the 4th power plus 3x squared plus 4. Looks kind of like an elm. So even though it has 6 possible zeros, how many actual zeros do we have? Yeah, we have 2, which would be positive 2 and negative 2. So 2 and negative 2. Those are our actual zeros, so we would write that as negative 2, positive 2. Or you can do plus minus 2. How many turns does it take? Yeah, that's 3 turns. And what is the end behavior? How do we describe the end behavior on this? So it falls to the left and falls to the right. So it's down, down. I'm going to put falls to left and right. In parentheses, down, down. So remember, with an x to an even power, the leading coefficient, the degree is 4. So that means it's going to have the same end behavior. And then this negative tells us my end behavior to the right will be down because it's negative. So since it has to be the same, it's falls to the left and falls to the right. Okay, so let's do the example that's on the packet. There's an example over here that explains it. Explains one problem. So let's do this one. List all possible rational zeros of 3x to the 4 minus 11x cubed minus x squared plus 19x plus 6. So we look at our constant term and we look at our leading coefficient. So you do your constant first. Constant, there we go. Can't spell very good. It's a 6. So what are the factors of 6?
1, 2, 3.
Mm-hmm. And 6. And we put that over the top of our leading coefficient, which is 3. So our factors of 3 are plus minus 1 and plus minus 3. And so we now write out all of our possible combinations. So you do 1 over 1, which would just be plus minus 1. 2 over 1, 3 over 1, 6 over 1, right? Those are all of the constants. So 2 plus 3 plus minus 6. And so that's with the denominator of 1, the leading coefficient factor 1. And so now we need to do it with our denominator of 3. So plus minus 1 over plus minus 3 would be 1/3, positive, negative, 1/3. And then we could do 2/3. What about 3/3? Is that unique? 3/3 is 1, so that's not unique. So we wouldn't need to write that down. What about 6 over 3? What does that equal when you simplify it? 2. So that's not unique either. So this is it. So these are all the possible. So how many are there? Well, we have positive, negative. So it'd be times 2. So 12 possible. Okay, let's go back to our notes real quick. Okay, we are going to use synthetic division to find a possible zero. So we found all the possible ones, but we need to actually determine out of those possible ones which one actually is a zero. So I'm going to use our example from our paper that we had. So we have 12 possible zeros. And it's these are the list of our possible zeros. Okay. So we need to find out which ones are actually zeros. So we're going to use synthetic division. Yesterday, when we used synthetic division, we determined if it had a remainder like this one, 3 was not a zero of it because you have a remainder. It doesn't divide it evenly. So anytime you have a zero remainder, then the number that you did over here would be your zero. So what we have to do is we have to actually try different numbers to see which one comes out with a zero remainder. So I'm going to do a little bit of a calculator pre-work to see what our actual zeros are so that we can come back to the synthetic division. So let's go ahead and put this in. Okay, did I put it in correctly? Sometimes I make little mistakes. Okay, so we're going to go to the graph and see where does it cross. Oh, lots of numbers. So if we go to second calc, find a zero. Let's say we want to find, well, we could actually just hit trace. What would this one be? Let's see, zoom in a little bit. So it looks like it's at 1 and then, or -1. And then another one, let's see, trace. What would that one be? Should be -1/3. Zoom out. And then we have a couple more over here. 2 more over here. That one looks like what? What is that one and that one? Y'all tell me. Second.
2 and 3.
Yeah, it looks like 2 and 3.
Oh, I kind of went to the second table or second graph, and then if you go to the table, if you look on the line side or zeros, you can still find the number.
Oh, okay. As long as they're whole numbers. Yep, that works too. Okay, so we know that these are the zeros. We found them in the calculator. In order to show using synthetic division, you would do synthetic division with your numbers that are the possible zeros, so all of these, to determine which one's an actual zero. So we know that -1 is an actual zero, so I'm going to show you how we would use the synthetic division to show that. So you put the -1 in the box and then do your coefficients in descending exponent order. Okay, so we carry down the 3, and we multiply -1 times 3, and then add those together. -1 times -14, add those together. -1 times 13, add those together. -1 times 6, it's -6, add those together, 0. So since this is a zero remainder, that means that -1 is a 0. So let's say you didn't have a calculator, you didn't have access to the calculator, then this would be an easy way to show that it's a 0. It doesn't take very much to do this. So then to find another number, let's say we had to try out 1. So let's see how 1 is different. So do 1. So then we would carry this down. We do 3. That'd be 3. That would be -7. -8. There we go. Then -8. -9. -9. 10. Is this right? 16 the remainder? Okay, so since 16 is the remainder, 1 is not a 0. So after you divide and you find that 1 works, or one of the numbers works, so like -1, it worked. So we know that that one's good. Then we could try another number, but we can use this now, which makes it a smaller problem to deal with. So I'm going to use this one for 2, because we're actually dividing. So 3, -14, 13, 6. We're going to show that 2 works and gives us a 0 remainder. So this came from whenever I did the synthetic division. This was what was left over, or this was the polynomial that came out after you divided by the -1. So this would be 6. That would be what, -8? -16, -6, or -3. And then when we multiply, we get -6, which is 0. 0 remainder. So that means 2 is a 0. So we've showed -1 and 2. So you might have to try ones in between this if you didn't use your calculator to check them in the beginning. Then let's do 3, but we're going to use 3 with what we got here. So now it becomes an even smaller problem. So it'd be 3, -8, -3. That's 3, negative. No, that'd be +1. And then that'd be 3, that'd be 0 remainder. So 3 is a 0. And so what's left, this means 3x plus 1. And so we set this equal to 0 and solve for the last x. -1, -1. 3x equals -1. Divided by 3. So x equals -1/3. So -1/3 is a 0. Okay, so that way we were able to come up with each one of these. by using the synthetic division and then breaking it down even more. So anytime you get a number that's not a zero remainder, then that's not a zero, so you can move on to another one. Okay, let's look at this problem. F of x equals x cubed plus 4x squared minus 3x minus 6. So we need to find out all the possible zeros so we can start trying them. So we're not going to use the calculator to begin with. We're just going to go ahead and try it out. So we would do the constant term, the factors of -6. And did you say positive -6? Yeah, 'cause 6 will go into 6. And then we put that over factors of our leading coefficient, which is 1. Positive -1. So really our possible zeros are positive -1, positive -2, positive -3, and positive -6, because dividing by 1 isn't going to change anything. So why don't we try 1 and see if that works? So we do the synthetic division. So list out your coefficients. So carry down the 1. 1 times 1 is 1. 4 plus 1 is 5. 1 times 5 is 5. Add those together, you get -2. 1 times -2 is -2. Add those. No, that's supposed to be a positive. Okay. And so that gets -4. So my remainder is a -4. So 1 is not a 0. So then we can try -1. -1 times 1. Add those together, we get 3. -1 times 3 is -3. Add those together, you get -6. -1 times -6 is +6. -6 plus 6 is 0. So that's good. That means that -1 is a 0. So let's look at what we're left with. Let's write this as a polynomial. So this is our constant, this is our x term, and this is our x squared term. So it's x squared plus 3x minus 6. So we need to solve this. So we could do what? The product of -6, that gives us a sum of 3. Is there one? No. So how else could we solve this? So we know it's not going to be perfect. How else can we solve a quadratic like this? Yep, quadratic formula. -b plus or minus square root of b squared minus 4ac all over 2a. So that'd be -3 plus or minus square root of 3 squared, that'd be 9, minus 4 times 1 times a -6, it'd be plus 24, over 2 times a, so over 2. -3 plus minus square root of 33 over 2. So that's, and that can't be simplified. So that's, our solutions are -1, and then -3 plus square root of 33 over 2, and then -3 minus square root of 33 over 2. Okay, let's do one more. We're not going to do number 5. We'll do, or 4. We're going to do 3. So x cubed minus 2x squared minus 11x plus 12. So we need to list out our possible rational roots. So we want the factors of our constant over factors of our coefficient, 1. So that'd be plus minus 1, plus minus 2, plus minus 3, plus minus 4, plus minus 6, and plus minus 12. All over 1. So it's just those same numbers. So as long as they are real, we can find them on the calculator. But let's go ahead and just try with 1 and see where we get there. So we'd have 1, -2, -11, and 12. See if it's a 0. 1, 1. Add those together, -1. 1 times a -1, positive 1. -1. Add those together, get -12. 1 times -12 is -12. Add those together, we get 0. So 1 is a 0. So then what we could do here is look at this as another polynomial. This would be your constant. This would be your x. This would be your x squared. So x squared minus x minus 12. And we can see if we can solve this. So what has a product of -12 and a sum of -1? Three and 4, right? The bigger number would have to be the -4. So that means we can factor this to solve to get our 0. We solve these, and x equals -3, and x equals +4. So then our solution is that one that we have, the -3 and the 4. We list them in descending order, so -3, 1, and 4. And those are our zeros. So you may have to go through a few numbers if you're unsure about what it could be, because we could have started with -1 and solved. -1 doesn't work. Then we have to go from there. Okay, you're going to work on this section and last section as your assignment. And that is all the notes for today.